Hey, time's to start. Thank you all for coming. My name is Arun Majumdar. I'm in the Mechanical Engineering Department. I'm kind of new to Stanford, and our new dean, Persis, has put me to work right away. So this is part of the strategic planning effort that my co-chair, Jennifer Whittam, and I are engaged in right now, is really about the future of the School of Engineering. We have a fantastic committee, and some of the committee members are here. Do you want to raise your hands? The committee members, all here? Fantastic. And we are going through, this is part of the engagement, is going through an effort right now, and we'll have two department chairs talk about what the future of their department is all about. A little bit of the past, but mostly about the future. And this is the early part of an effort, of a much longer effort, of what we're going to engage in. And what we're really after, and this is by May 15th, we're going to deliver, really after is, what is the future? That is, what are we going to look like 10 to 15 years from now? And as part of that, what's the vision, number one? And part of that, what is in that vision? You know, are there some new themes? Can we be ahead of the game? And when Persis asked me about this, I said, okay, is there a calibration? Can we calibrate this? Has this been done in the School of Engineering before? And apparently it has not been done. But from my own experience, my field is in the area of energy. I can say that Stanford has made a big dent. And Stanford did this before any other campus or university did this, is really focused on energy and climate, and out of that came a GSEP. And this was ahead of the game. It was not a zero-sum game. It really put Stanford on the map. It brought in new resources. People changed the directions, research direction. Students got engaged. New faculty got hired in that direction. And after that, many of our peer institutions said that, oh, we should do something. The United States got interested in energy. The presidential campaigns got talking about energy, hopefully, and climate. So that was a game changer in many ways, and where Stanford was ahead of the game. Now we are asking the question, not to be complacent about where we are today, but what are we going to do in the future that we could be ahead of the game, of new trends that are coming that we should be looking at, and organize ourselves and position ourselves to be successful. And that's what we want to be 10 to 15 years from now. So this is part of the effort. This is the early stage. We'll have a lot more engagement with students, with faculty, with staff, with alums, with donors, and a lot of others. But this is very important because we want to hear from you all and from the department chairs where you are thinking going forward. Jennifer, do you want to add something?
Talk about the survey and the appetizers.
That's right. Very important. First, the appetizers. The reception is going to be right outside in the Earth Sciences building? Hardly. That's right. Thank you, Hardly. I'm still learning about where the restrooms are. Okay, that's where it's going to be. And there's going to be an email to the faculty, and this is an experiment. The faculty are the guinea pigs. It's an experiment we're going to try of, what are we calling, the pulse feedback, getting the pulse. And this will go out in the email, a little question, the 3 questions. And in fact, Allison, you want to say something about this? Quickly.
Sure, so this quick, very short questionnaire will ask you, as you think about the School of Engineering and what it means to you, to ask what you like, what you wish, and what if something were different. It's very open-ended and a way for the committee to get feedback about the School of Engineering.
Great. And we are aware that there could be some feedback and survey fatigue, so we want to minimize it, but we also want to hear what you have to say. So you'll see a few more of these coming out, but we'll plan it out in a way that it's not too burdensome. So let me stop here and hand over to Paul. Future of Material Science.
All right, thank you. Actually, I'm all mic'd up.
Okay, you're all mic'd up.
Doubly mic'd.
Do you have this? Oh, you got double. Oh, this is for you then.
Yeah. Okay.
going to do a time check here. It's 4:09, so I'm going to try to get through this in 20 minutes to leave time for questions. And let's project it. There we go. Yeah. Like that? Or no, not like that. Okay, looks good. All right, so I appreciate the opportunity to share some ideas we have about the future of material science and engineering here at Stanford. I'll spend a few minutes just setting the stage for where we are right now, but I want to focus most of the attention on the future and what we think the opportunities are for our department. So just a quick current snapshot. Mainly I want to impress upon you the exciting demographics of our department. We have a total of, I think, 17 names here, and the bulk of them are concentrated in the mid-career category. We also have 4 early career faculty members, so we have a lot of people who are at a point now in steady state where they're really building reputations as the leaders in their respective fields, and 4 early career faculty who are coming up and building their groups and also garnering a lot of attention, and then senior leadership as well. So I think we have a great demographic. In addition to these core faculty members in the department, we have connections to many other departments on campus, within the School of Engineering, within H&S, at SLAC, within the School of Medicine, and these are represented in part through 16 courtesy faculty appointments that we've made over the years to recognize these many connections we have and the interdisciplinarity of a lot of the things that we do. Furthermore, we have 6 consulting faculty. So I wanted to say it's not going to be an opportunity to highlight everyone's work or even a fraction of it here, but I wanted to point out a few examples of contemporary work by these individuals, just to give a flavor for some of the breadth of interests we have. So characterization of materials is a very strong, a great strength at Stanford, and a consistent theme in a lot of the things that we do. Bob Sinclair has been one of the leaders of that, the leader of that in our department for many years. And his group is famous for its work in a technique called in situ electron microscopy, where you can look at materials under reactive or operating conditions and see how they evolve and change, often at an atomic level. So this shows some work he's done studying the oxidation of carbon nanotubes inside an electron microscope. It's a very challenging kind of an experiment, but he's one of the world's experts in this. Professor Sean Wong, who's joint with the electrical engineering department, is a faculty member who is focused on magnetism, and particularly magnetism at the nanoscale, and many different aspects of that. One of the important ones from a device perspective has been looking at magnetic nanoparticles for tagging molecules and cells in biological contexts or biomedical contexts, and his group has developed things like magnetic sensors for mobile health monitoring. Evan Reed is an assistant professor in the department. He's a computational scientist and has been modeling materials so he can understand them fundamentally without having to actually make them physically. And this is a great advantage because these things are often hard to make, but study their properties in a computer. And one of the things he's been focusing on are these very interesting 2D layered materials. They're basically just a few atomic layers thick. They can be made in the form of a monolayer. And then by deforming them or changing their structure mechanically, we can induce changes in their electrical properties. So they can go from being semiconducting to metallic simply by folding this sheet. And his group is studying that and trying to understand how to, what the potential outcomes of these things are. Will Chu is another assistant faculty member, and he's an expert in solid-state electrochemistry, so sort of high-temperature electrochemical processes that occur in many different systems. One of the ones he's been looking at is how to combine sort of traditional semiconductor materials with high-temperature ceramics to make electrochemical devices for generating fuel, for example. So that's an introduction to the department and the demographics. We should say a little bit about where we are located physically on the campus. So we're centered here in these buildings, right around here, right around Skilling. The Duran building, which we share with AeroAstro and SCPD, and the Jabal Lab for Advanced Materials. It's an independent lab that's housed in these 2 buildings, McCullough and Moore, and we share those buildings with applied physics and physics. So because we're in a situation where we share space with other departments, there's a lot of interaction, there's a lot of opportunities for collaboration that result from this, and it's also something that carries over in our interactions with other parts of campus. So in this diagram, I'm trying to show the relationships that we have to many other departments in the School of Engineering and also outside the School of Engineering in this area, where there's a lot of faculty members who are interested in materials research for one reason or in one system or another. So in addition to these two buildings, we have, as I said, courtesy faculty members across campus. We're engaged in co-advising relationships, and we have active collaborations with faculty from across the university. And also, we're involved in leadership of shared facilities. So shared facilities, because a lot of our experimental work is very instrument intensive, shared facilities are really critical to materials research. We need state-of-the-art instrumentation for characterizing materials. We need to be able to fabricate things in a reproducible way. We're involved in many of these shared facilities across campus, and in addition have leadership in independent labs and affiliates programs. Say a little bit about the statistics for the department. So there's been a great evolution and a great renewal of our faculty that's occurred in the last decade, and we really have Jim Plummer, who's here to thank for a lot of that. He gave us the opportunity about 10 years ago to renew our faculty after we spent a lot of time developing a vision at that time for the future of materials at Stanford, and it was one that allowed us to hire new faculty members and really revolutionize what we do as a department. So we added some faculty members, which was great, and we also in the process have expanded the number of students, PhD, MS, and bachelor's degree students. We rolled out a new undergraduate program because we had more bachelor's students interested in the major. And there was a really amazing transformation in our research. So this is one way of measuring research productivity. It's archival journal publications in a particular year. So we had a total of about 50 of those in 2005 and almost a fourfold increase 9 years later. And in parentheses here are the journal articles in Science and the Nature series went from 0 to 23. So there's been just a tremendous increase in productivity and impact in our research as a result of the new faculty members we've hired and have come up through the system and are doing great things. Also, of course, with this increase in publication totals, we expect there must be more funding involved to pay for all of this, and in fact, the funding volume has increased by about a factor of 3 in the last decade. This is sponsored research funding. So there's been a tremendous transformation that occurred as a result of us being given an opportunity to renew our faculty and sort of re-engineer what we do as a department. So if we look at what we actually do, this is one way to do it. If we think about the materials science and engineering faculty, there are really 3 kind of major themes that most of our research could fit into. One of these is what I will call a push, which I think is the language that we received in an email from Arun. So this is where some new capabilities, new understanding allows us to go out and try to do new things that could have an impact, but it's not quite clear how it's going to play out in terms of solving a societal problem at this point. So nanoscience and nanotechnology, there are all these new tools and methods for doing things at very small scales, controlling them, characterizing them. So that's a push, and there's a lot of us who are involved in nano. Just about everybody in the department is doing something related to nano. A big pull is renewable energy technology. So just about in fact, every faculty member, I believe, in the department has some activity in renewable energy technology. So it's a big aspect of what we do. And then in terms of a third major theme, life science and biotechnology. This is a pull. We're being pulled by needs in human health and the demographics of the developing world, of the developed world, and the changes in the developing world. So bio is a big part of what we do as well. And as you'll see, it's something that we think is going to grow in the future in the department. In terms of what we actually do in our research, the methods that we use, material scientists have traditionally looked at their discipline as involving 3 things. The structure of materials, which dictate their property, and then synthesis methods that we can use to modify those 2 things and control them. So synthesis, structure, and properties, that's what we always think about. I'm breaking that up a little bit differently here to synthesis, characterization, which is the measurement of the structure, modeling, which is prediction of what these structure-property relations should be, and then devices. And this has been a huge change in the way we operate in the last decade. We've really become a department of device builders. There's a tremendous amount of device fabrication that goes on hand in hand with all of the other engineering science that we have traditionally done in our discipline. So why do we do that? Well, materials are needed to enable state-of-the-art devices. In many cases, we need to have to understand how materials behave at a fundamental level to make a state-of-the-art device. So we often want to have atomic level control, and therefore we have to characterize materials to achieve that. We need to have synthesis methods that give some control in structuring. It's often exquisite structuring. And we want to be able to design and fabricate devices that work, and we need a fundamental understanding often to do that. So this is one example. This is two different cross-sections through a nanowire field effect transistor in a transmission electron microscope. And you may not be able to see these dimensions here, but these are really small. So this is a nanowire that's 12 nanometers across, so it's maybe 100 atoms or a couple of hundred atoms across. And the control of the orientation of this thing, its interface with surrounding materials, the abruptness, the chemistry on an atomic scale is really, really important to how these things operate. So you have to understand those things at a very basic level to make them work properly. Another canonical device of contemporary technology beyond the field effect transistor is a solar cell. There's a tremendous amount of interest in photovoltaic energy conversion. And this is one example of a thin film solar cell. And I just want to point out the number of different layers that are involved here and the complex chemistry and control that's necessary in the structuring of these things. It turns out that the active part of this device, which is what shines here in this EBIC image, is the interface between this layer and that layer. So knowing exactly what's happened there, the structure and the composition, is critical for this to operate efficiently. So we need to understand those things, and that's really what we do in our department. We try to understand how the materials and their structure influence function in devices. And this means that science, the discovery of these new materials and understanding of their properties, has to go hand in hand with engineering. Hence, we have both in the title of our department. Materials cost is a critical factor, so we want to think about cost because these are engineering technologies we have to worry about. And we also need to think about devices because they're very sensitive probes of how the materials work. So in addition to understanding materials to make great devices, we make great devices to understand the materials. So what do we think are the future opportunities in our department? So these are what I'm calling engineering grand challenges. There's a whole list of these that NAE has come out with. There are 14 of them. I've tried to aggregate them in ways that we think in our department make sense for us. Some of them are of less importance than others, but I'm going to concentrate on these four, which we think are very important, and we think we can play a role and be leaders in these four areas. And I want to start out by saying that clearly these are big problems. Sustainability is a huge problem. Human health. We don't expect to be the only department doing this. In fact, we encourage collaboration and hope to be a part of a major effort involving multiple departments within the school and beyond the school in these areas. But we think we have something important to do in these four areas. So I'm going to go through them each very quickly and talk about where we think we have a role to play in these various grand challenges. So in the sustainability area, there's a lot of different aspects to that. Energy is a huge part of it. Environmental impact and how to quantify it, how to reduce it. Water is a huge issue, availability of clean water. Agriculture is very important, obviously. In our department, we have a current strength in energy materials and science and technology. Really, as I showed, that's the one thing that just about everybody in the department works on. And there's a lot of exciting work going on in that area. I'm showing 3 examples here from Itsue's work on battery materials, Jennifer Dionne's work on hydrogen storage and nanoparticles, work from Mike McGee's group on novel materials, new materials for solar cells that are very efficient. But there's a lot of opportunities that we're not really addressing at the moment and where we think we can, in the future, have a big impact, building on the foundation of this kind of work that we're doing already. One of them is in materials for the environment, broadly conceived. And that involves things like understanding how to synthesize and characterize at a local atomic level catalysts, materials for membranes, photoelectrodes that are needed to couple the sun's light into driving various kinds of processes. And these are important for things like water disinfection, purification, and chemical transformations. So there's a lot of these kinds of problems that are important and growing in importance, and we want to play a role in them. So in the case of, I got a sun here that's appeared out of nowhere, but in the case of sustainability, we have an example that I'm interested in, I know something about it, I'll say a little bit about it. Once again, this is just an example of many different kinds of problems that we can address here, and it's an example where there are a lot of interests across campus in many different parts. So this is just one example where I think we can play a role. Achieving efficient storage of solar energy as fuel is potentially a game changer for grid-scale solar power, but it requires a lot of new materials. Efficient, selective, cheap catalyst materials for chemical transformations. There's a lot of these different catalysts that we could be interested in for things like oxygen evolution, CO2 reduction, ammonia synthesis. Earth-abundant semiconductor materials that do not corrode under extreme conditions, because if you're going to split water to make oxygen, there are not that many semiconductors that can stand up to that in an actual device. And so we need to do clever things to allow them to be stable. Things like ion-selective membrane materials that are used in electrochemical reactions and that are transparent. We need to let the light through, but they're highly conductive for selected ions. So there's a lot of fundamental science and prediction that can be done in this area, and there's a lot of this going on at Stanford already to try to identify the best materials for these applications. There's clever work to try to protect Earth-abundant semiconductors like silicon by using new techniques like atomic layer deposition to coat them with pinhole-free corrosion-resistant layers. We nanostructure these expensive catalyst materials, so we use them very sparingly, and we worry about how to connect them all together in a device with a membrane separating two parts of the device with different half reactions occurring in them. So it's a very nice example of bringing materials together and implementing it in a device, always being guided by what we learn about the materials. Another horizon for us is new tools for science. So here we're basically developing this emphasis on instrumentation, finding new ways to develop new functionalities and new techniques. Current strengths are chemically sensitive electron microscopy. So this is some work from Will Chu's group where he's looking at battery materials and how they locally are lithiated during operation inside of electron microscope. And there are great opportunities afforded by major instrumentation such as at SLAC, the LCLS, which is this incredible, unique, bright bright light source, pulsed light source for X-ray analysis. So I think there are future opportunities where we combine high spatial resolution with high time resolution. This is an ultra-fast workhorse, but we can use it in ways that can allow us to look at things at an atomic level in very short time frames. That's a very exciting opportunity. And also in situ characterization of things like material synthesis or device operation. So an example then, we can perhaps use this pulsed high flux electron beam from the LCLS for sub-picosecond diffraction and imaging. And there's some initial work going on this right now at SLAC, and it's something that we can play a role in. And I think it has opportunities to give us real space imaging of atomic motion and local structural changes in device-relevant materials. It's going to provide unprecedented direct insights into things like engineering material synthesis and evolution. So these are some examples from Aaron Lindenberg's work, looking at things like an electron diffraction pattern as a 2D material goes through a phase change, going from an insulating to a metallic state, and the change in the actual crystal structure in sub-picosecond time resolution. So the opportunity to really watch these things happen in real time, I think, is very exciting. The third horizon we see where we can have an impact is the broad area of human health. And here the drivers are aging, global economic development, and also the closer coupling between medicine and engineering that's enabling a lot of new possibilities. So currently we have strengths in biosensing and separations, in cells and tissue as engineering materials, and also in drug delivery. But we see future opportunities for remote healthcare monitoring and careful drug dosing, rejuvenation, materials that rejuvenate adult stem cells, and targeted drug therapies that are done with designer materials. So there are a number of examples that we can point to here. but remote health monitoring and drug dosing could provide life-saving care for emergencies and low resource settings. So this is one of the areas in which we think we can play a role. And it's really materials dependent. We need materials that will interface with tissue and sense biological signals, biocompatible materials, so the chemical stability is very important here as well, and then reliable self-actuating materials that can do things like release drugs on demand. And these can have applications in terms of sensing neuron activity, being able to chemically sample from cells using nanostructures like these nanostraws, and also developing specialty microparticles for drug delivery. And the final one I want to say something about, where we think we have a role to play, is materials for novel computation. So traditional computational approaches driven by scaling, Moore's law, seem to be coming to an end. There's a slowdown in Moore's law. There's been a tremendous amount of materials understanding that has underpinned this shrinking of devices to molecular scale dimensions. But it's getting harder and harder to keep doing this. And so this Moore's law scaling relationship, right around 2010, started to slow down significantly. And one of the key reasons for that is the cost of continuing to shrink the device size. And fewer companies that have the sales volume to cope with the capital costs of setting up and running new factories to do this. So there's a lot of interest in alternative or novel computational schemes, and some of these involve innovations in materials. So I want to point out particularly the possibility to learn from how the brain works, so developing materials that enable neuron sensing, biological neurons, to help make neuromorphic devices and neuromorphic circuits out of artificial materials. And then also the possibility of silicon-compatible quantum computing that can also leverage important materials innovations. So one example here then is an objective would be to develop organic semiconductor materials that can be used in conformable, implantable electrochemical transistor sensors that can monitor neuron activity in the brain, and then from that understanding help develop materials that are useful in things like resistant switching or neuromemristive responses that can be used for artificial synapses or configurable neuromorphic circuits. And finally, silicon-compatible qubit materials to enable quantum computing, which is faster for certain kinds of operations than our classical computers. So there's a number of different materials and structures that we are interested in this space. It's a real opportunity for our department to play a role in terms of leveraging our existing work in new contexts. So thinking about that and then looking forward to the next 10 years or so, this suggests we're going to have to make some additional moves to boost and renew our faculty. We have a plan for hiring priorities that map onto these different areas. One of them, of course, materials for a sustainable future, materials for novel computation, materials for human health, and then three priority areas, which are really cross-cutting. If we don't know how to do these things well, we really can't impact these other problems very effectively. So materials characterization, this is a cross-cutting topic where we're interested in developing new tools for science, as I said, computational material science and engineering, so new predictive capabilities and methods, and new methods in material synthesis. We have to be able to make these materials in order to be able to achieve the practical ends that we wish. So the last thing I want to say something about is space. So we talked about hiring, and that means we need places to put these bodies and the activities that they will engage in. So this is where we're currently located. Right here, that's Durand, and that's the McCullough-Moore complex. And so what we propose, this is our space aspiration, is a relocation of some part, or perhaps all of what we do, to a different part of campus where we're closer to electrical engineering and the School of Medicine and Sri Ram and those places, because we sense the need to do a lot of this work in collaboration with close-by colleagues, and to be involved in the development of new facilities that all of us are going to need to work on these kinds of problems. So in a 10-year horizon, we'd like to move into new space in this part of campus, nearer to these departments. How that's done and to what extent that involves moving existing people versus new people is to be determined. We want to co-locate with materials and device-centric faculty members from across the School of Engineering and perhaps from other parts of campus as well in this new location. And we want to be co-located with new shared facilities for characterization, fabrication, and not just the traditional sort of nano facilities, which are amazing and which we want to keep strong and strengthen, but looking at facilities where we can characterize and make things across a broader range of length scales. So pulling back a bit from nano and atomic and looking at more the micro or mesoscale, which is also very important. And I think that combination, co-location with new facilities and with faculty colleagues, will make for a very strong mix. So thank you. Oh, sure.
I have a question.
Yeah,
If we go back to your hiring priorities.
sure. Oh, wait a second. Okay.
Yeah.
Yes.
They fall into different categories, and maybe it's this push-pull thing again. But would you run a search materials for a sustainable future? Or would you run a search for a material scientist and, be happy if they're working on a sustainable future? And wouldn't some of your current faculty be migrating into areas of interest? So it's a strategic decision whether to be driven by these applications or by core science.
Yeah, it's a great question, and it's one that we often struggle with. I think the way to do this best is to have a broad search. Broad searches have worked very well for our department, and I think across the school. I mean, the broad searches have been amazingly successful. But to have words in each of these broad searches where we call out one or two really strategic areas where we're most interested in receiving applications. Now, ultimately, we're going to go with the best athlete. We're going to select the person who comes through the door and just impresses us the most. And whether they're working in that strategic area or not in a particular search is to some extent secondary. But we want to focus on these areas, and we want to cultivate contacts across the world of other institutions where people are working in these areas and really encourage those applications. And we may want to think about senior hiring moves as well, targeted opportunities to help seed expertise in areas where we don't currently have it. Although we've done so well with recruiting junior faculty members and bringing them up through the ranks, I'm reluctant to not keep doing that. Yes.
How many faculty do you expect to hire over this 10-year horizon, and do you expect your faculty to grow, or is this going to be?
Yeah, we expect that we think we need to grow. Some of these areas are ones in which we just don't have any strength at the moment. Others we do, and so the actual numbers, could be as many as 6, or it could be fewer than that. And we may, be interested in searching jointly with other departments, where the winning candidate, if it were a junior professor, could select among them for their lead department. So these are there's not necessarily a one-to-one mapping between faculty positions in these priority areas. They're just the kinds of areas we're going to think about as we put together search ads in the future. Yes?
I had a question just about your students, and you showed how many PhD and masters and undergrad, and where do they go?
Okay.
Are the masters, is that on their way to their PhD, or is there a big demand for master's students in material science to go out?
Yeah, most of our master students go out and take jobs, immediately after getting the master's. Some will apply to other institutions for PhD programs, and some will petition to join our PhD program. That will happen for a small number every year, a couple of people who are really outstanding academically and who have an avenue through a research project with a professor to actually get a PhD.
So there's a cohort of masters, like the profession needs the master's.
That's right, yeah. So it's really viewed as a terminal degree. I hate that word. It sounds like it's an illness, but it's not viewed as a stepping stone to a PhD in our program.
And then the undergrads, do they pretty much have to get a master's to get?
Many of them decide to co-term. Some of them go out and take jobs right out of school. Some of them go to grad school in other places. A few of them stay for the PhD program, although we don't, we don't try to hold on to our people. Yeah. Any other questions? All right, thank you.
You may want to turn off your...
Hooked up so many different ways here.
So we are getting the videos on the web. I think the video from last week is now up on the SoE-Future website. And we'll be posting the slides as people cooperate and email them when asked.
Oh, yeah, I have... yeah, I think so.
Abbas was convinced he was going to have problems with this projector, I think, based on a checkered history. Oh, there we go.
Okay, good afternoon. My talk will be in two parts. The first part will be a very quick overview of the department, the present, and then the longer part will be talking about a strategic plan that we've been putting together over the last 2 years, which we call EE21. EE21 does not refer to a class, although some people actually thought it was the name of a class. We may actually have an EE21. I don't know if we do or not, but that's not what I'm going to talk about. Okay, so first part. EE is one of the largest departments on campus. We have 58 active faculty. I'm not counting here consulting or what are they called? Right, yeah. Just real faculty. 600 PhD students. We graduate about 85 a year. About 200 master's students, about 140 bachelor students. And it's a very research-oriented department, expenditures of over $45 million a year. And we look at the department in two ways. One way is as core disciplines, which we group into three large areas: physical technology and science, hardware and software systems, and information systems and science. And these areas are quite overlapping, quite a bit. So they're just a conceptual way of looking at the department. And the physical technology and science faculty and students live in Allen and Spilker. The hardware and software systems people are mostly joined with computer science, and they live in the Gates building. And the information systems and science people live in the Packard building. And there are some people here that don't live in any of these, but not too many. So there are many examples, and I can spend the rest of the evening talking about examples of the amazing disciplinary research that goes on in these areas. So I'll just do some quick rundown on some of them. World first nanotube digital VLSI, quantum repeaters, world most efficient high frequency power converters, ant-size radios, laser accelerator on a chip, full duplex wireless radio, software defined networks, computer cluster management tools, distributed optimization, and the list goes on and on. The other way we look at the department is as a conduit for multidisciplinary research. We have many faculty involved in projects that address major societal challenges, jointly with other engineering departments, with departments in humanities and sciences. We have about 15 faculty that have joint projects with the School of Medicine, and in fact, some people even talk to School of Business. We have, out of the 58 Faculty, we have 25 joint faculty with other departments, CS being the big one, but MS&E, MSE, and there is a difference between these two for those of you that these are not the same department. Statistics, and so on. And 30% of our PhD students have co-advisors from other departments, which is an interesting feature. So again, there are many examples of amazing multidisciplinary research in healthcare, medical imaging, neural prosthetics, wirelessly powered implants, nanophotonic probes for cancer detection, all the way to analytics for medical records. And in energy, solar cells, we haven't actually been super active in the energy area, but we are building it up. Solar cells, thermoelectric devices, nanophotonic passive cooling, and smart grids. And urbanization, we're even starting, Balaji Prabhakar is starting to dabble into, actually much more than dabble now, he's all full in, doing things like in transportation and stuff like that. Okay, so now I'm going to spend the rest of the time, and since I stand between you and the refreshments, I'm going to be very quick. So you're welcome to ask me any questions you want. First, the plan that we put together is really the result of some very fundamental challenges that not only face the department, but face the EE as a field, right? So we are kind of in a funny part of our life here as electrical engineering. So I'll talk about that a little bit, and then I'll talk about what EE may or should look like in the 21st century and what we as a department have been doing and still need to do. Okay, so before we talk about the 21st century, let's take a step back 100 years. EE in the 20th century, this is the golden age of electrical engineering. Key contributions to electrification and digital revolutions. Electrical engineers used tools from math and physics, collaborated with scientists and engineers from other disciplines to design and build many things, including electric grids, wired and wireless communication systems, digital computers, integrated electronics, sensing and imaging systems, and so on. However, the recent focus, meaning in the last 40 years, has been on riding the CMOS scaling freight train to build smaller, ever smaller, faster, and cheaper computing and communication systems. EE tools, of course, have had many applications outside EE, but this was not the cool thing to do if you are in EE. The cool thing to do was to ride the CMOS scaling freight train and its applications. Now, there are some challenges. There is really a perfect storm, actually, for this field. First, CMOS scaling freight train is coming to a screeching halt, as Paul nicely. By the way, one difference between my talk and his talk is he has much nicer graphics. I was too lazy to. Graphics just take too much time to. So Moore's law, which we have been relying on to drive scaling of information technologies, cannot really be continued very much longer. However, at the same time, the needs for information technology scaling have never been greater. And that's because of the incredible demands of what you call Internet of Things, which is a bag of stuff that every few years there's some kind of an acronym that people are excited about. Now it's the Internet of Things, and big data, of course, has been around for a while, so it's no longer very exciting. So the Internet of Things is envisioned to have 1 trillion connected things versus billions, which we have now. So that's a huge, 3 orders of magnitude more devices. And this presents enormous challenges. For example, the Internet of Things devices must consume very low energy, otherwise you're going to burn down the planet. But current devices still, relatively speaking, consume a lot of energy. Trillion devices cannot be all battery powered, otherwise there will be huge businesses in changing batteries. Like the biggest service companies will be running around changing batteries 24 hours a day. So battery is not the future. And there's another question which is quite interesting actually, is how do you design and manufacture millions of different things? I mean, we're used to designing maybe thousands of things, right? How do you design millions of things? So the current design fabrication methodologies cannot really handle these kind of enormous number of things to be designed. So we need a new methodology. And finally, maybe not finally, but another very important concern is that trillion devices, if you think we have it bad now in terms of security and so on the internet, just wait until we multiply the number of devices by a factor of 1,000. So, okay, now the exabytes of data, which I don't know how many zeros exabytes is, but it sounds like a lot of zeros. So, from the Internet of Things, medical records, and on and on, also present huge challenges and require us to keep scaling information technologies. Questions like how do you store and process exabytes of data without burning down the planet again? Current physical technologies consume too much energy, again. And current, this is very important, which is current von Neumann-based architecture, which we have been stuck at for 60 years, are also very energy inefficient and not very well suited for the new types of things that we want to do. And just to add more, current networks also consume a lot of energy. So finally, how do you analyze and optimize with exabytes of data? That's, of course, a very important challenge as well. Now, so at the same time that Moore's law is coming to a screeching halt, we have another big problem, which is that the NAE 21st Grand Challenges are not in traditional EE areas. And I think I have a theory about that. I think it's because none of the people on the committee were actually from EE. So that's kind of killing our field, basically. This may not be a joke, by the way. So they are in areas such as healthcare, as Paul articulated, sustainability, urbanization. But addressing these challenges will need both existing and future information technologies. In fact, many of the Internet of Things applications that people talk about are driven by societal challenges, and many big data applications are also driven by them. So they go hand in hand. So what do we envision EE? In order for EE to sustain its successful history, if it were to sustain its successful history, we need to actually look back at what are our core strengths relative to other fields. And I think our core strengths are a combination of the ability to build very complicated systems. We are very intellectually very broad and very flexible. We just jump on stuff whenever we need it. We don't have any problems learning new math, new physics, new chemistry, whatever it takes to get the job done. And finally, our tradition or culture of multidisciplinary research, which has really been going on forever, from the very beginning. So we need to leverage these to do two things. So this is a two-pronged approach. And the pull and the push, I think, come in here. I didn't use these words, but so one is to create scalable physical technologies and architecture and system to serve the needs of the Internet of Things and big data. And at the same time, use existing and new information technologies to build application domain-specific systems, which are called ADS systems, which address some of the NE grand challenges. So let me say a few things about each direction. So in terms of building scalable technologies and system, basically what's needed is ubiquitous intelligent system that sense, organize, classify, and extract information from the deluge of data in real time. So that requires new highly scalable, energy-efficient architectures, and brain-like architecture are very tempting. But these people have been talking about this since I was born. I mean, there's nothing, von Neumann wrote something about the brain and the computer or something. So, but we still haven't done it, right? So it's not. New physical technologies and new wearable cyber-physical biological interfaces with orders of magnitude lower energy. And you can see lower energy is coming up on and on and on and on and on. So this is a huge thing for our field. In terms of application domain-specific systems, in healthcare, I think EE can contribute in two specific areas. Maybe it can contribute to other areas, but there are two specific areas. One of them is to build smart implantable medical devices that collect real-time data from the body and directly assist it through drug delivery, electrical stimulation, and so on. In particular, electrical stimulation is very interesting. It's something coming up now that's called electroceuticals, where people are talking about treating people with electrical pulses instead of killing them with chemicals. So I hope that works out. That would be great for us, actually. The second thing is to build systems that help shift diagnostics from major medical facilities to doctor offices and homes, like lab on chips, handheld diagnostics, and so on. In sustainability, EE should play a major role in building a smart grid that, with pervasive sensing, communication, computing, and low-cost power electronics to not only deal with energy efficiency, but deal with renewable energy, storage, electric cars, and all these kinds of things. We also have a role in building intelligent edge networks, like intelligent buildings and so on. In urbanization, I think one of the things that I think will be huge in the future is using information technology to monitor and control urban systems. I think that's a humongous, and if I were to pick a big thing that I would talk about, it's really this. I mean, we have all these amazing information technologies, and we have these incredibly backward societal systems, right? And somehow these two need to come together. So what's needed to achieve this vision? We need to create stronger and broader collaborations within EE, with other fields, and with industry, and this comes in every thing I talked about. We need to foster a maker culture in EE. EE originally was a maker culture. When I was young, we used to build all the sorts of stuff. We stopped doing that because everything now is you write some code and stuff. But now I think there is a need to come back and start building things. And there are two reasons for that. One is rapid prototyping to understand and optimize complex systems. And the second is to extend the democratization of do-it-yourself making and manufacturing to electronic systems, which of course has been very successful in mechanical engineering. The other thing that we need to do is reinvent EE curriculum. We need to introduce applications and making early. We need to provide the student with flexibility to learn how to apply EE system to address major societal challenges. We don't know much of that. And then finally, we need to teach the basic tools of EE that are useful in many, many fields, like control signal processing embedded systems, and also something about sensing, computing, and networking to all engineers in the same way that now all of them learn about programming. Finally, we need the facilities that can meet the needs of these things. So what have we been doing? As you have seen from the beginning of my talk, our faculty students are already creating new technologies and systems and contributing to the NE Grand Challenges. We are actually creating new collaboration through the Stanford System X Alliance, the Stanford Data Science Initiative, and the Secure Internet of Things Initiative. We are actually have been redoing our undergraduate curriculum, and there is a lot of information about that through our webpage. So what much remains to be done, however. We still, hiring is still our #1 priority in embedded systems, big data, energy, bioelectronics. We also need to strengthen our connections to chemistry and biology, or chemical engineering and bioengineering. We've just scratched the surface on developing the new technologies and architectures and these things. We have done a little bit. We're not known for them. We need to support the development of System X. These are all budding systems, and create more collaboration with neuroscience and ChemH Institute. And of course, there's a lot still to be done in the undergraduate curriculum. Finally, we need to modernize our facilities. We need 21st century shared fabrication facility to support the development of the new technologies and system, 21st century instruction labs to support the new curriculum, to foster the maker culture, 21st century student and common spaces, foster greater collaboration, and house the new initiatives. And this is, I just thought I would tell you, if you haven't heard about this, we already have a proposal to build 3 new shared labs in the Allen building, in addition to SNF, and we have names for everything. So fast turnaround facility, system prototyping, bioelectronics and biosensor lab, and SNF will shrink a little bit, but will be better. So what would EE look like in 10 to 20 years? I think that what would make EE really successful in 10 to 20 years is to have fundamentally new computing architecture beyond von Neumann, and to also have it's not replacing CMOS necessarily, but what is the next CMOS, right? We need a driver. We need something to drive. As I mentioned, we really do need to keep scaling. I mean, otherwise the economy itself will come to a screeching halt, I think. In terms of EE as a conduit of we'll be playing a major role in revolutionizing various aspects of healthcare, sustainability, urbanization. And I think 10 to 20 years from now, hopefully the maker culture will be in full swing, and the EE curriculum will be much broader, will be appealing to a much broader set of students, even outside engineering. That's it. So I think I broke records, right? Okay. So, yeah.
So, but this might sound like a facetious question.
Oh, no.
Plenty intended to be one. So it's always bothered me a little bit that when we talk about ourselves as engineers, we're always talking about providing sort of services, or being a leader and providing kinds of tools and services and devices that society needs. And I think by and large we do a good job of it. But when you talk about revolutionizing healthcare, right?
Right.
And you talk about, okay, we're going to invent the next generation of devices and tools, and whatever the healthcare professionals need in order to, create a better human life. But why wouldn't the goal better be, what's EE's role in making healthcare more affordable? That should be the goal.
Yeah, and that's the underlying. Yeah, I agree with you, and I think that's an underlying.
But that's the way we should be approaching.
Sure,
It's not like,
absolutely.
What can we do to help sustain,
Right.
Essentially a system
Right.
that's not really.
No, you're absolutely right. You're absolutely right.
And I think it applies
For everything else, yes. Yeah. There's a bit of humility that is needed in these things, right? I mean, it's kind of hard to say we're going to revolutionize healthcare. I mean, EE is not exactly the center of healthcare. I mean, we are going to help them do what you're saying more than anything else, right? Now, if something like electroceuticals become real, then we actually are in the center of it, right? So it's hard to, right? I mean, I'm very comfortable with the core, but this area it's going to be a little bit of, some of it may be opportunistic, some of it may be luck. You never know. Yes, yeah, sure.
On the first one,
Yeah.
I mean, I think people have been talking about where's the next switch.
Right.
And we were just talking about it as well.
Yes.
And what's the new qubit?
Yeah.
And 10 to 20 years actually is not a very long time
No.
to talk about scaling.
Right.
things.
Takes forever.
Right. So if you are to see this happen in the next 10, 20 years, there are probably about 6 or 7 different options today for
Yes.
qubits. Or
Right.
there are people talking about
Right.
switches of different lines.
Right.
Of those, I think, so I'm wondering, the question is, has the EE department looked at that and said, you could throw that out, because that's never, for obvious reasons, that's not going to scale.
Mm-hmm.
But here are 2 or 3 options that you want to focus on, because that's where most likely it's going to happen. Has that happened?
I think there was a time when we were going to throw everything away. So the thing is, at least in the last 2 years, we tried to not do that. I mean, really, I'm serious. I mean, people just said, look, it's done, hardware is done, devices are done, and let's move on and write software. I mean, that's basically was the message that was, but to answer your question, I think the stuff that Philip Wang and Subhash Mitra are doing is really very interesting. It could be a little bit evolutionary, but some of it could be revolutionary, and time will tell. Because they are actually building, out of these devices that people didn't think will do anything, right? So they are trying to actually build small systems. So that could be an interesting direction. There are other directions that are very interesting, like the large-scale electronics, which is very different, from this, that are extremely promising, and I think they're going to happen or happening already. Now, quantum is really, I like to call it the sleeping giant. When it wakes up, I think a lot of things will happen, right? So that's the one that we're not doing enough in. We really aren't. We're doing some, but we tend to be a little bit, because we're in engineering, we tend to be a little bit grounded. It's just like, what is this nonsense, right? But at some point, that nonsense will not become nonsense anymore. And we want to be there, obviously. So that's one of the areas that I think is really, quantum, I think, is a really interesting direction. And I talk a lot to Yelena about this, so it's kind of a, yes.
I find it interesting that you mentioned that a little bit of humility is needed. If you look at cochlear implants, or retinal implants, or spinal cord stimulators,
Sure.
or even cardiac pacemakers.
Right.
These are all things.
Yeah.
And probably are all good examples of what you're calling electroceuticals.
Electroceuticals, yeah.
So what's the point of all these buzzwords, and what is exactly new?
I think Ada Poon is sitting here, and she's doing some work on that. The idea in electroceuticals is much more fine-grained, targeted pulses to specific cells in the body, which is not exactly what we do today. What we do today is kind of, Exactly. So it's basically, instead of chemicals going and, the problem with chemicals, you go everywhere and create havoc, in the body, right? And if you can localize the treatment, I think it could make a huge difference. Yeah.
I wanted to ask you about your slide on curriculum when you said that the EE curriculum should be something which, most students
Right.
are taking at the same level they take coding. I thought that was an interesting statement because it's my own observation of trends and requirements has
Yes.
been in the other direction. Like we're actually kind of removing requirements overall in most departments and giving students much more flexibility in their majors. And I also found it interesting because obviously if every department said that our curriculum needs to be required of the students, we would have a serious.
Oh, no, we're not. I'm not saying our curriculum.
So actually, just the question was,
Yeah.
the question was, do you think that, more broadly, do you think that the trend towards flexibility is sort of taking us away from thinking hard enough about what students need to be learning? Like, I think you got to that statement by thinking about something that's missing if we follow that trend through.
Yeah, it's a long conversation. We've spent so much time talking about this stuff. I don't know if I can say it very quickly, but if you look at departments like, for example, civil engineering or something, and you see what they're trying to do, and you'll hear about that at some point, right? They're trying to install sensors in everything, and right, and and do control and do signal processing, but they don't know anything about this stuff. Right? Now, requiring them to take our 100-unit curriculum is too much. And the question is, the challenge is, how do you distill these things? Just like CS has been able to do this for programming. Everybody learns programming. They're not great programmers when they're done. I mean, with all due respect, right? I mean, they know something about programming. I mean, my son took 106 A and B, and he's not a very good programmer. So, so it doesn't turn you into a great programmer, but it's the same level, right? We don't have anything like that, right?
What did
That's
he major in, double E?
No, he majored in chemistry.
Oh,
Yeah.
checking.
No, he majored in chemistry. He tried double E and dropped out because of E40. So. Which we are changing, by the way. So finally. Right. So any other? Okay, thank you.
Well, I have a suggestion again for the cocktail party part of this, so we have something to talk to each other about. So as we said, there's going to be a very quick survey going out probably tomorrow. And we're sending it first to the faculty. If that works out, it'll go next to staff and probably students. It's just 3 little boxes with prompts for each box. You don't have to fill in every box. We were asked to suggest how long it will take you to do the survey. I think it will take under 2 minutes to type in the box, and then unlimited time to think about what you want to put in the box. So somewhere between 2 and infinity minutes to fill in the survey. But you could get started by talking to other people over appetizers about what you want to put in those boxes. So the prompts for the 3 boxes, one is I like, okay? One is I wish, and the third one is what if. And you can fill in any or all of those boxes, so now we can go over and chat with each other about what we might put in those boxes. Thanks.
Thank you.